On this video, we will do a couple more examples regarding the convergence and divergence of infinite series. So let's start by looking at this introduction question. And it states, so let's take in consideration this infinite sequence. It's just a sequence. We don't know if it's geometric or arithmetic. We just know that it's a sequence. And what we want to do is we want to use a decimal activity, which if you were to scan this QR code, it will take you to the decimal activity that we're going to be using in a second. But what we want to do is we want to see if the infinite series as sigma a of n, if it diverges and converges. And again, the way that we determine if a series converges or diverges, and what I mean by series, I mean infinite series. So an infinite series converges if the sequence of partial sums converges. And again, if you were to write down the first partial sum and the second, and then the third, and then the fourth partial sum, and then the fifth partial sum, and so on, if we see that the sequence is converging, then we can state that the series is converging. So that's what we want to do. So how do we get those values? Well, first, let's take a look at our actual sequence. So let's go to decimals and let's just plot the sequence. So here we have it for example 1. Here we have the, let me just erase all this. Cool. So here we have the function that we want to analyze, or at least the sequence that we want to analyze, 3 times 1/2 exponent n minus 1. So that's what we do have here. 3 times 1/2 exponent x minus 1. So now let's start by just plotting the sequence. So if we just take a look at the sequence, here it's stating that the first term, I don't know why this keeps doing this. So here, what it's stating is that my first term has a value of 3. My second term has a value of 1.5. My third term in the sequence has a value of 0.75. My fourth term has a value of 0.375. My fifth term, we're just going to go all the way to 6. So my fifth term is 0.18. And lastly, my sixth term has a value of 0.09. And again, we want to just see the sequence so we can see that it's a sequence that seems to be decreasing in value when we're moving up on terms, but we don't use the terms to determine if the series converges. What we need to use is the actual partial sum. So for that, here our second row, it is the partial sum. So let me see if I can just. But before we take a look at our partial sum, now notice that, like kind of like how we said it seems that we have a sequence that is decreasing. So if we were to plot our sequence values, notice that yes, the sequence seems to be decreasing in values. But now let's take a look, like we said, now let's take a look at the partial sum. So for the partial sum, here we have the following. So let me just erase the sequence. Now let's take a look at the sequence of the partial sums. So my first partial sum is the value of 3. And it makes sense because if we add the first term, then obviously the partial sum is 3. So now, what is the second partial sum? Well, that's the addition of the first two. 3 plus 1.5, which is 4.5. Now, if we take a look at the third partial sum, which again, the third partial sum is the addition of the first 3 terms. So if we were to add those 3 terms, we would get a value of 5.25. Now let's take a look at the partial sum of the fourth partial sum. So here we have fourth partial sum, which is again, is the addition of the first 4 terms. So that will give me a value of 5.6. And we're just going to do this until we go to the 6th term. So the 5th partial sum is 5.81. And lastly, the 6th partial sum, which is if we add the first 6, my result is going to be 5.9. And again, what we need to do here, and keep in mind what we're doing here, we want to determine if the actual series converges. So therefore, to see if a series converges, we got to take a look at the sequence of the partial sums. So the question that we want to answer is the sequence of partial sums converging? I mean, if we take a look at the values, we go for 3 to 4.5 to 5.25, 5.6, 5.8, 5.9. And notice where we are, 6. Here's the 6. The 7 partial sum is 5.95. The 8 is 5.97. The 9 is 5.98. The 10. Now notice that, yes, they still are continue increasing in value, but are they approaching a certain value? Well, let's keep going. Let's find the 50th, 5.999. Now let's find the 16th term. The 60th partial sum is 5.999. And if we take a look at the behavior of the sequence of the partial sums, the sequence seems to be converging to the value of 6. Because notice that it seems that we're still increasing, but it's just getting closer and closer and closer to the value of 6. Notice it goes 5.9. It seems to be stuck in a 5.9 because it just started getting closer and closer to 6. So therefore, yes, this sequence, yes, the sequence, the sequence of partial sums, it seems to be convergence to the value of 6. So now, therefore, we can make the following conclusion. Now we can say that we have this infinite sum, the infinite sum of a of n, which again, if we want to write it explicitly, that's the infinite sum of this big sequence. It seemed to be converging to the value of 6. Now, one strategy to see is the following. So I know that my conclusion derives from the analysis that we did to the partial sums. But when is it that the partial sums seem to be converging to a value? Well, the partial sums seem to be converging into a value if the sequence itself is converging to 0. So that's an observation that I would like for you to notice, that the partial sum or the sequence of the partial sum will converge definitely when the sequence itself is converging to 0. Because if the sequence is converging to 0, then the partial sum, you're going to just start in values, you're going to be adding values that are 0. So therefore, you're going to be getting stuck in a very specific value, which in this case, the value happens to be 6. So let's do one more example. And again, this is going to be a little bit different, but the idea, it is still the same. So this, we're going to do a couple of steps here. It says take in consideration the given infinite sequence. So we know that a of n, it's an infinite sequence. And the first thing we want to do is we want to write down the infinite series. So at least for a, we just want to write down the explicit expression for the series that we're going to be taking a look at. And notice that the series here is sum of n, because the sequence itself here, it is defined as just n. So that takes care of a. We just wanted to write down an explicit expression of what we're doing. We want to write down the infinite sum of just a sequence that has been defined as just n. And what we want to do is we want to write down the sequence of partial sums. So let's write down the first 6 terms of the partial sums. Well, in order for us to write down the sequence of the partial sums, we need to know the value of the first, second, third. Let's go all the way to 6 one more time. But now notice that if the sequence is being defined as just n, then the value of the term is just the term number. So a of 1, my value is just going to be 1. A of 2, here n is 2, so therefore the value of my term is 2. A of 3 is 3, 4, 5, 6. So we need the terms themselves in order for us to find out the partial sums. So now let's actually find out the partial sums, because that's what we wanted to do here. We wanted to write down the sequence of partial sum. So let's find the partial sums. So that's the first partial sum, that's the second, that's the third, that's the fourth, that's the sixth, that's the fifth, that's the sixth. So the first partial sum is just adding the first term, which is just 1. The second partial sum, it's adding the first 2 terms, which is 3. The third partial sum is adding the first 3 terms, which is going to be 6. The fourth partial sum is the addition of the first 4 terms, so that will be 10. And the fifth partial, and if we continue doing this, the fifth partial sum is going to be 15, and lastly 21. So let's just confirm that this is actually true. So let's go back to our Desmos activity. Now we're taking a look at example 2, and yes, it seems to be correct. So here, if we were to plot our sequence, notice that here, if we plot just the sequence itself, just the terms in the sequence, notice that we get this pattern, which again, it seems to be increasing without a bound. And if we take a look at the actual partial sum, so the first partial sum is 1, then the second is 3, then the third is 6. So notice that it just agrees with what we found out by hand. So here it is. Now that we got that, so the actual sequence, the sequence of partial sums, it's going to look like 1, then followed by 3, then followed by 6, then followed by 10, then by 15, and then by 21. And there's too many after that. Okay. So now that we know the sequence of the partial sums, which is what we wanted to do here, let's want to sketch the sequence of the partial sums. So here we add our sequence itself, but that's not what we want to graph. We want to graph the partial sums. But what do we notice here? Well, we zoom out, and again, I'm not going to graph it here in here because we do have the graph here. So here we got, so this is the location of the first partial sum, the second, the third, the fourth, the fifth, the sixth, the seventh, the eighth, and the 9. And again, if you're still confusing as to how we get in those locations, but the way that we would locate it here, there's a coordinate point. Oh, okay, so the pen's not working. Cool. So the location of this point is 1, 1. That's why you do see it all the way here. The location of the second partial sum is going to be 2, 3. Then followed by 3, 6, which would be about here. Then 4, 10, which is about here. 5, 15, which is about here, and so forward. So that's how we are plotting those values. But most importantly, what do we notice? Does the sequence of the partial sum seem to be converging or diverging? Well, notice that it seems like the sequence of partial sums is a divergent sequence, because notice that if we plot it, it seems to be just increasing without a bound. It doesn't seem to be approaching a specific value. And look, if we plug in more values here, notice that the column of the partial sums is just going to be increasing without a bound. Notice, the 14th partial sum is 105. The 15th partial sum is 120. If we were to plot it, you can start seeing that it's just gonna continue to increase without a bound. So therefore, the sequence of the partial sums is a divergent sequence. Now, if the sequence of the partial sums it's diverging, then what we can say is that the actual infinite sum of the infinite sequence, which again, we wanted to just take a look at the sequence to just be n, this quote unquote is going to be equal to, in some sense, infinity, because it's just going to be increasing without a bound. So we're just going to say that the infinite sum diverges. So we say that's just going to go to positive infinity. Now notice that the last thing that they're asking us here is to verify that the results that we got here actually can be compared to the sequence of the partial sums. So this is a sequence that we can get algebraically, but again, we're not gonna discuss it in class how we get into sequence, but all we want to do is, well, does the sequence of partial sum actually get us the values of the partial sums? Well, I don't know, let's graph it. So if we scroll back here, here we have the equation x plus 1 over 2. So that is the sequence. So now what we want to see is, well, does this actually give us the values that we got for our partial sum? Well, the first term of the partial sum is 1. Yes, that agrees. The second partial sum is equals to 3. Yes, that agrees. The third partial sum is 6. Yes. The fourth partial sum is 10. Yes. The fifth partial sum is 15. Yes. The sixth partial sum is 21. Yes. So yes, in this case, we just verify that this expression can be seen as the sequence of partial sums. And the reason why I'm putting this down here is for you to see that there are times that we can have a sequence defined in any way. And then by doing some algebraic manipulation, which we're not going to do in class, we can define a sequence of partial sums in an explicit formula. And we're going to take a look at a small example in our next lessons ahead. But at least for now, I just wanted for you to realize that there are times that we can actually represent the sequence of a partial sums in an explicit formula. So hopefully this was helpful. A couple more examples for you to get a better idea about the convergence and divergence of infinite sequence series. And this concludes our lesson for today.